Building a mass driver on the moon is the key to humanity's future in space because the moon is a giant ball of feedstock material already in orbit around the Earth, and a mass driver is what allows us to use it as such. All lunar activities, all industrialization of the moon and ISRU processes and energy generation and vehicle fleets, etc. are all towards this purpose, all to serve the mass driver. For this is what allows us to use the moon for what it is. But the mass that makes up the moon is in a somewhat useless orbit naturally, so we just have to go there and carve it up into smaller packages, which we can then launch on a mass driver to more utilitarian orbits. By filling Earth's orbit with lunar materials, we can decimate launch costs and construct whatever we want. Think about all the benefits we get from space today. Delivering lunar mass to Earth's orbit would allow us to multiply those effects by 1,000, by 10,000, by 1,000,000. A mass driver on the moon would have a real and measurable impact on your life, not just your nation's prestige or some rich people's profits. Megatons of mass in orbit around the Earth allows for the creation of mega orbital infrastructure, which will magnify humanity's access to space, our capabilities to do more things in space, and the benefits of space that we're able to bring back down to Earth. Too vague? Okay, fine, here's some specifics. Space stations, telescopes, AI data training centers, power satellites, fuel depots, habitats big and small, public and private, Mars colonization fleets, semiconductor manufacturing facilities, organ printing facilities, biohazard labs, strategic resource acquisition capabilities, internet and climate and strategic satellite constellations, sunshades for science and climate, cryogenic labs, advanced microgravity enhanced composite manufacturing facilities, national defense and power satellite constellations, just to name a few. To be clear, we can probably do most of these things without lunar mass. Access to orbit is getting cheaper every day. But lunar mass makes doing these things much less expensive, which means we can do much more, much easier, on much larger scales, much more quickly, with much less politicking. I never like comparing lunar development to historical European colonization of the New World, but since Apollo, people have been trying to find the reason we need to go back and develop the moon. And the proposed incentives are always just a reincarnation of the historic colonial model of gold, silver, spices, except now it's gold, silver, uranium, helium-3, and living space. When Europeans found gold and spices and good lumber and new crops in the New World, all these things were major boons to their 15th century economies. But today, our 21st century economies are not wanting for gold and spices and lumber and crops, at least not enough to justify the distances that have to be traversed and challenges overcome with the lunar development. If we found tons of gold and spices and good lumber on the moon today, it wouldn't lower the market price of those things on Earth, since importing them back here would never be competitive with the gold, lumber, and spices grown on Earth today. Our modern economies don't need more spices and gold and crops. What they need is orbital infrastructure for energy and communications and information and security and science. Those are the exotic spices of today. And infrastructure requires mass, so the gold of the moon, that magical element that will set in motion the great leap beyond this Earth, is the moon itself. Bulk mass. And a mass driver is our treasure galleon. But I'll be real with you, we always like to portray space as a transcendental endeavor that can only do good for all mankind and saving the sea turtles and printing organs and curing cancer and all that marshmallow fluff. It is all that, but it's also the case that Sputnik was a hollowed out nuclear warhead meant to send a message, and Wernher von Braun spent a decade developing ICBMs before the Saturn V. Space, like everything humans do, has always been, is, and will always be a double-edged sword. And while this channel does focus on the bright sides of the future, and definitely hopes for a better future, the reality is that there is a realpolitik side to lunar development that cannot be ignored. And it's hard to overstate, so I will just state it outright. Whoever controls the moon will control the world. And it's pointless to control the moon without a mass driver. So really it should say, whoever has the most mass drivers on the moon controls the world. This is not just about O'Neill cylinders and sea turtles. This is about the world order. It's about who has a say in what. It's about growth, prosperity, and standard of living. or a lack thereof. Want to protect your country from existential nuclear-tinged consequences by building a golden dome? Orbital pebbles are the best solution, and to do that, you're going to need a lot of mass in orbit. What better place to get it than the moon? With ample mass in Earth's orbit, you can build nuclear defense and offense just as much as you can build private space yachts, or communist habitats, or giant telescopes, or climate-saving sunshades, or paperclip maximizing AI monstrosities. We keep talking about the race to the moon with China, and we say we're going to set up a permanent base and maybe mine some ice and some craters or something. But why? What does this do? Are we gonna bring back more moon rocks? We have about 400 kilograms, more than enough for science and prestige. We don't need more moon rocks brought back to Earth. What we need are more moon rocks brought back to Earth orbit. We've pricked and prodded and scanned the moon for more than 60 years with various satellites and rovers. Knowledge is great, but it's marginal at this point. How many more rocks do we want to collect in labs? When are we going to start collecting rocks not in labs, but in orbit? Everyone is focused on AI as the determining factor for the next 100 years, but I guarantee you the first thing a super intelligent AI will do when it wakes up is build a mass driver on the moon so it can access the unlimited energy and resources of space. The race to the moon is not a race back to the moon to prove we're still number one. It is a race to a lunar mass driver to determine who will be number one. There are a lot of different ways to turn electric energy into kinetic energy, and so there are a lot of different types of mass drivers, and each design is a big topic. So this will be a series. Today's video will be on railguns, the next will be on coil guns, then we'll discuss quench guns and linear induction launchers. Those are the big four, the top contenders, but there are others and alternatives such as spin launchers and rocket sleds and light gas guns. However, I cannot promise I'll cover those since I personally don't think they're as good as the big four for a few reasons. Namely, the fact that they achieve basically the same result as the big four, but for a greater cost and complexity either upfront or over time. There are specific cases and niche contexts where they might make sense, but they are more narrow and I think less likely than the set of contexts covered by the big four, and being meticulously exhaustive can be exhausting. If we're not having fun, what's the point? So all I can say for now is we'll see how far we get, but I can promise, or well, indicate my willingness to at least cover the big four, starting with we call these systems guns because that is what the technology behind them was originally invented for, but when used as a mass driver, they're only guns insofar as rockets are missiles. I think a more accurate way to think of these is as motors rather than guns, as they use the electromotive force to turn electricity into kinetic energy. But the idea of it being a gun does help us conceptualize some aspects of the system, such as the payload being like a projectile, even if it exponentially increases the chances of this video becoming demonetized. Railguns work using the Lorentz force to launch a projectile at extremely high speeds without the use of explosives or chemical propellants. The system consists of two parallel conductive rails connected to a power source. A conductive armature bridges the rails and holds the projectile. When electric current flows from one rail through the armature and into the other rail, it generates a powerful magnetic field around the rails. This magnetic field interacts with the current in the armature to produce a force perpendicular to both the magnetic field and the current direction, accelerating the projectile forward. But this explanation sucks because it doesn't explain what's actually going on. Why does electricity create a magnetic field, and why does it repel the projectile rather than attract it? Well, the answer has to do with balls and contracted length. Imagine there's nothing in this universe except two balls. One starts moving, but which? From the red ball's perspective, it appears that the blue ball is moving, and from the blue ball's perspective, it appears the red ball is moving. Relativity. Length contraction is a strange aspect of special relativity that's often described using extreme examples such as a spacecraft moving near the speed of light or some object falling into a black hole. But it happens to everyday moving objects as well, especially when it's cold outside, albeit at an infinitesimally small amount. The red ball doesn't just appear to be moving relative to the blue ball's perspective, it also appears to become slightly smaller along the axis it moves. It contracts. Why? Math. Relativity. I don't actually know. If I had to guess, I'd say that this is the Universal Physics Engine's version of MIP mapping. But it's not very noticeable. If something was moving at 150 kilometers an hour or 93 miles per hour, then to a stationary observer it would appear to contract by roughly a picometer, or roughly 1/100th the size of a hydrogen atom. So we never notice this phenomenon in everyday life, but we can notice its effects. When we connect a positive terminal to a negative terminal, electrons begin to move towards the positive terminal. Contrary to popular depictions, they don't move very fast. In a wire with a diameter of about 1 millimeter, the electron's velocity is about 4.4 millimeters per minute at about 1 amp, and about 22 millimeters per minute at about 10 amps. That's very slow, and why it's typically referred to as electron drift rather than something like electron flow. Because of this movement, even though it is slow, the electron's reference frames are decoupled from those of the protons, and to the protons, the electrons appear to become length contracted by an infinitesimally small amount. Now, if there were just 1 or 2 or 10 billion electrons, this wouldn't matter. But there aren't 1 or 2 or 10 billion. There are roughly 86 trillion electrons per cubic centimeter of copper wire. 86 trillion ever so slightly length contracted electrons. It is enough to cause a slight density imbalance of the electrons in the reference frame of the not moving protons, slightly more negative charge than positive charge. But because like charges repel each other, there is an almost instantaneous correction to this imbalance and the electrons push away from each other, effectively creating more space, and thus restoring the lower energy state neutral equilibrium. But not all electrons are winners in this density correction. This displacement forces some to the surface of the conductor where they would be repelled out of the conductor if it wasn't for the work function holding them back. This creates the surface charge pattern, a localized buildup of negative charge at the surface of the wire. And since there are more electrons near the negative terminal of the conductor, this negative surface charge pattern is stronger near the negative terminal. A stationary charge very close to the conductor would feel a very slight negative electric field. However, since the positive terminal is depleted of electrons, the net charge of the wire remains neutral. This electric charge from the surface pattern is distributed along a gradient, decreasing in strength the closer it gets to the positive terminal. And then, near the positive terminal, a positive charge can actually be felt from the slight increase in proton density relative to electron density. So the wire is neutral in total, but not at local areas near the surface of the conductor. But this is an electric field, and it is very weak. To be felt, a particle has to be very close to the conductor's surface, and it is not what creates the magnetic field felt by a moving outside observer. However, I made a point of discussing how this surface charge pattern arises because the felt magnetic field arises from the same reference frame decoupling that causes the surface charge pattern to arise. The magnetic field arises from the same relativistic principles felt by an outside observer. If a charged particle outside the conductor begins moving in one direction, let's say in the direction and at the same velocity as the electrons, then from its perspective, it will appear that the electrons are at rest and it is the protons that are moving, and so they become length contracted, and so there are slightly more protons. The density is off, and a slight positive charge is felt. If the outside particle is positively charged, then it will be repelled by the wire. If it is negatively charged, then it will be attracted to the wire. If the outside particle moves in the opposite direction, then it will still appear that the protons are moving since they are at rest. but it will appear that the electrons are moving even faster, since they're moving in the opposite direction. To the outside particle, both the protons and electrons appear to have a slight length contraction, but since the electrons are moving so much faster than the protons, the electrons contract more, so there is a net negative charge. If the particle is positively charged, then it will be attracted to the wire. If it is negatively charged, it will be repelled by the wire. But what has actually happened is the outside particle has length contracted itself due to its own movement. But to it, it appears like the other particles are the ones moving and therefore length contracted, just like the red ball sees the blue ball as moving and vice versa. The observable result is that we have a force that attracts and repels depending on which direction an outside observer is moving, and for all intents and purposes, this is a magnetic field. But we can see that what looks magnetic in one frame can look electric in another. Hence, magnetism and electricity are unified, and we call it an electromagnetic field. Moving faster and or increasing the current increases the amount of electrons or protons that are length contracted relative to you. Maybe you can think of this as the volume of decoupled reference frames, and so we get a stronger magnetic field around a wire. Cables next to each other whose currents are running in the same direction will attract, while cables with currents running in opposing directions will repel. Why? How is this working? Well, from a relativistic standpoint, if the currents are running in the same direction, the electrons in the moving wire see a length contraction from the protons in their own wire and the protons in the other wire, but not from the electrons in the other wire, since they are moving at the same speed. So there is nothing countering the perceived increase in protons from the other wire, and thus there is a net positive force felt, and so the negative electrons are attracted, and so they attract. The same and opposite is true for each item in the wire. We can just as much tell the same story for the protons or the electrons in the other wire, but with opposite charges. And the inverse of this is true if the currents run in opposite directions. But this relativistic matrix is a lot to juggle and think about, so we just simplify this happening as a magnetic field. Look, if we take a cable and run a current through it and put a compass next to it, then the needle head will point in a certain direction as the electrons and the magnet align themselves with the field around the cable. If we do this on all sides of the cable, forming a complete circle around the wire, we can trace the direction in which the magnetic field flows. And this is where we get the right-hand rule. Let's look again at cables that attract each other, this time with magnetic field arrows. In the middle, we can see the arrows point in opposite directions. Their magnetic fields interfere and cancel each other out. But on the outside, they persist, and so there is an energy density imbalance, a low energy density area between the cables, and so the cables are attracted. You could almost think of them as falling into an energy density hole together. This hole created by their fields interfering and canceling each other out. Their lowest energy state is when they're together. It takes energy to keep them apart. If, however, the current in the cables runs in the opposite direction to each other, then the vector arrows align, the fields can be thought to amplify each other, and there is a swelling of energy density between these cables that is higher than the energy densities on their outside, and so they are repelled from each other. This is a common schematic shown in textbooks to describe the Lorentz force in terms of energy density changes through interference or amplification. The force exerted by a magnetic field can be said to move from the north to south, positive to negative. A wire with a current running through it is put into this field. Behind the wire, the fields amplify. In front of the wire, the fields interfere. There is an energy density wave behind the wire and trough in front of it, so the wire moves forward, both propelled by the wave and pulled into the trough. This is how the Lorentz force actually works, and it gives us electric motors. In a railgun, when we complete the circuit, the magnetic fields look like this. Look what happens in the middle of the circuit. All the fields amplify each other. We have 3 ups, and so we have an intense energy density amplification here. This swelling of energy density wants to push all 3 conductors away from each other, and if we do nothing, it will, and the circuit will break. However, we can lock the rails in place by nailing them down to some ballast, so only the projectile will be forced forward, propelled by the energy density wave pushing against the rails anchored in place. The more current we run through it, the stronger the energy density wave. The more force, the faster the acceleration. By the way, these principles of energy density amplification and interference are roughly how an Alcubierre drive is supposed to work. Anyways, that's how the Lorentz force works. Was that level of detail necessary? Absolutely. Here at Anthrofuturism, we're not like the other girls. We obsess over details to the point of obnoxious irrelevance. We get lost in rabbit holes so deep we make Alice look organized. What the f was I talking about? Oh, right. Alfred Thayer Mahan's The Influence of Sea Power Upon History. He who controls the seas controls the world. Or was it the moon? Wait, why is the Navy interested in railguns? Oh, okay. So the military has been interested in railguns for decades, mainly as a way to shoot down ICBMs, since railguns can potentially shoot projectiles at missile distances much faster and cheaper than missiles, and railguns can be made compact enough to put on a ship, truck, or even a plane. This means railguns have quite high tech readiness, TRL-7 for a ship's gun. However, I should note that since TRL-7 is defined by being tested in the environment it is intended to be used in, and since we intend to use these on the moon in a completely different capacity on a completely different scale, railgun mass driver tech will obviously have a lower rating, so it's probably better to think of this military stuff as a high TRL rating for a similar yet adjacent technology, but not the same tech. Still though, we have data for real-life, full-scale railgun systems across different designs, and we know it can achieve the necessary velocities for orbit, while most coilgun demonstrations, on the other hand, remain laboratory scale with lower velocities for comparable masses. This is not to say coilguns should be ignored over railguns, they just haven't been nurtured as much by the unlimited money-printing, milk-making wet nurse that is the federal government. Maybe this will change now that Uncle Sam is interested in the moon again. But despite decades of suckling, most of these railgun programs were cancelled at the end of the Cold War, except for the Navy's, which was cancelled in 2021. The reason we don't see battleships bristling with railguns is mostly because the Navy's gun required 25 megawatts of electricity, but most destroyers, most of which are from the 1980s, can only spare 9 megawatts of additional electricity, and upgrading the electrical systems of Arleigh-Burke-class destroyers was found to not really be worth the extra cost, as it would require other weapon systems to be removed for lack of space. The only US Navy ships that could produce enough excess electrical power to get the desired performance were the Zumwalt-class destroyers, a program which was mired with problems and was itself curtailed. However, if railgun research had been allowed to continue, the main problem the scientists working on it were trying to solve was that of extending the barrel life, which was quite low due to ablation or rail degradation. Since direct current must flow through the armature, a reliable electrical contact is necessary. We can either do a large contact or a small contact, but there are trade-offs. Since the contact has to make contact with the rail, there is friction, and once you approach orbital velocities, this can become quite large, causing wear on both the contact and the rail. The Navy's program aimed for a barrel life of 1,000 shots, and by 2014 had reportedly achieved over 400 rounds per barrel in testing, although it's not clear if these rounds were fired at full power. The full 1,000 shot goal was never publicly demonstrated before the program was shut down in 2021. And more recently, Japan's railgun test showed a capability of reaching about 120 rounds per barrel. This is better than 120 missiles, but it's horrible compared to the barrel life of artillery pieces like the M777, which are typically around 1,500 to 2,000 rounds. Fortunately for us though, there are major differences between Navy guns and mass drivers, namely that as infrastructure rather than a weapon system, we have way fewer design constraints. First, we can try to minimize ablation by using cheap and expendable contacts. Spring contacts, either spiral or helical, could be quite easy to manufacture and would maintain constant contact with the rails while eroding themselves. Of course, some damage may still be done to the rails, but if we have a well-tested design, we should have relatively high confidence in wear rates and thus inspection and replacement intervals. But what if the contact isn't solid? In some advanced versions of the railgun, plasma is used as the contact, which causes very little wear on the rails. But this requires the use of an expendable gas, so it becomes closer to something like a plasma cannon than a purely electricity-consuming weapon, which was the whole point in the first place. Even if we were okay with this, what is essentially a fuel consumption expense, the only gas we really have in abundance on the moon is oxygen. But plasma oxygen is too reactive and would actually increase rail wear. I did actually find one reference which indicated ablation might not actually be much of an issue for us. And Manfred Ehresmann's, sorry if I mispronounced that, awesome thesis on mass drivers, there is a note claiming that ablation isn't really an issue until 2,400 meters per second. Lunar orbital velocity is about 1,700 meters per second, and lunar escape velocity is 2,380 meters per second, just under this limit. Unfortunately, I wasn't able to access the cited source since it requires DLR access, so I can only cite the thesis itself. But if true, it's great news for us. And if not, well, replacing cheap contacts with each run shouldn't be much of an issue, just a tiny increase in per flight cost. Second, unlike the Navy gun, we can make a grid solely dedicated to powering this thing. We don't have to ration our energy on a ship. We can have as much electricity as we want, assuming we can make solar cells and electrodes and other grid hardware on the moon, an extremely important subject we've talked about many times on this channel, most recently with legendary NASA scientist and founder of Lunar Resources, Dr. Aleks Ignatieff. And finally, to fit the railgun onto a ship, the system has to be made relatively small, which means extremely high acceleration. The Navy gun was just a few meters in length and accelerated the projectiles to 2,400 meters per second at about 50,000 Gs, which is insane. Of course its ablation was high, so were the Navy's constraints. 2,400 meters per second is lunar escape velocity. That's pretty much the highest we'd need for a mass driver. And in all likelihood, we'd want to launch payloads below this, to lunar orbit, where they can be captured by a spacecraft, which will take them to a more stable orbit under active power. But even if we did want to go all the way up to lunar escape velocity, we don't have to fit the whole thing on a ship. There's a lot of space in space, and so on the moon we can make the system as large and low powered as we want. We have the option to trade size for power. For now, let's just say we want to shoot our payload such that it has a ballistic trajectory with an apex, or apollune, of 100 kilometers. To do this, we need to accelerate the payload up to a velocity of 1,700 meters a second, or 1.7 kilometers per second. If we accelerate at a constant 1g, 9.8 meters a second, then to reach this 1.7 kilometers a second, our system would need to be 148 kilometers long. Accelerating at 5Gs, which is about the maximum rockets do, and the limit for many roller coasters, the system would need to be 29.6 kilometers long. 10 Gs would require 14.8 kilometers. 50 Gs, which is fine for most cargo, would put it at 3 kilometers. 100 Gs, which is totally fine if we're just launching bulk regolith, would put it at just 1.5 kilometers long. So what's better? Long and low powered or short and high powered? Well, at first, faster and shorter might sound like the best option. 1.5 kilometers sounds way more palatable than 150 kilometers, but the more power we use, the larger our grid will need to be, and at some point grid size will become more expensive than rail length. So there's some optimal trade-off point for any given payload size and target velocity. To find this, we need to measure mass, since we lack a market on the moon to easily translate actions into dollar amounts. Measuring total mass instead is a flawed surrogate, but can give us some sense of expense, since mass is stuff we have to refine and make and deploy. Mass is materials, energy, and time, and materials, energy, and time is money. Normally, I would explain all the math and logic used to figure out the optimal minimum mass system, which is 55 Gs, for a 100 kilometer target apogee, but it ended up being quite a lot, and would bore most people quite quickly, and this video is already quite long, so for sake of not getting too bogged down in minute details, I'll instead link a write-up in the description for you pedantic nerds to feast on. But anyways, the result gives us a mass curve like this. The higher acceleration the system is, the less mass overall, but only up to a point. Amps determine the mass of the rails, and the amp scale to the square root of acceleration, while distance is linear in power scaling. In other words, mass grows much slower than distance, so we have more mass per meter, but less meters overall with the shorter, higher powered version. But then power, which is proportional to acceleration, scales linearly with amps, so at some point the grid size and therefore mass takes over. So it is a parabola with a minimum mass. For our specific target velocity, 1700 meters a second, and payload size, which is 1 ton, with some grid assumptions, 5% efficient thin film solar cells and 1 kilowatt power density flywheels, assumptions which I think are realistic and are explained in more depth in the write-up, this specific mass minimum would be a system with an acceleration of 55 Gs. This will change with your constraints and assumptions. However, notice that this plot is logarithmic. It is a very flat minimum. Anywhere between 50 and 60 Gs is within 0.2 to 0.3% of the optimum. I also calculated the mass minimum for a 2000 meter a second velocity, close to lunar escape velocity, and it was 61 Gs. And for a velocity of 1600 meters a second, slightly below orbital velocity, the mass minimum system was 53 Gs, so this range is fairly consistent across useful lunar orbits. But specifically for the 100 kilometer 1700 meters a second orbit, the mass minimum system is 55 Gs, which would have a track length of 2.7 kilometers, a travel time of 3.2 seconds, and an average power of 1.53 gigawatts, a solar grid area of 22.5 square kilometers, a rail width of 1 meter, and a total combined mass of 11,333 tons. This analysis is pretty back of the envelope, and we didn't include the mass of the cast regolith ballasts and anchors or the cost of deployment, operating vehicles and stuff, so this is just a rough estimate. And I should mention, we found the mass minimum system, but mass minimum might not be the best thing to aim for. 1.53 gigawatts is a lot of power, and 22.5 square kilometers is quite the solar farm. Maybe terrain and geography limit the size of your solar farm. Maybe solar cell creation and deployment and maintenance across 22.5 square kilometers is much more expensive than aluminum rails, even if it costs less total mass. These are context-dependent unknowns, and this shows us the limits of just using mass as a stand-in for true cost. But hopefully this does give us some sense of the scales involved, the ranges, and what ideas need to be considered. In many previous videos, and in my first video on mass drivers, I chose to use this animation which shows a railgun driving an armature which serves as the launch platform for a cargo spacecraft. And something of this size could work with railguns. One of their big advantages is their quote-unquote open air design, which means our payload isn't volume constrained by the geometry of the mass driver like it is with coil guns. We could launch a cargo ship off the moon if we had enough rails and electricity. However, all of the calculations we've done in this video were done using a 1-ton payload, and this is equally viable. Just as we can trade power and length, we can also trade payload size, a third dimension. A smaller payload means less power, or if power remains the same, then the system can be shorter. And it's important to understand that smaller payloads doesn't necessarily mean less mass delivered per unit time, as lower power requirements result in faster grid hardware recharge times, and thus the launch cadence cycle time is increased. So many quick launches, or a few big ones. However, given that the forces on the rail, which will likely be aluminum, are proportional to the mass of the payload, the forces on the rails involved in launching a 1-ton payload are 10,000 times smaller than the forces involved in launching a 10,000-ton payload. However, we could just build more rails to compensate. And many small payloads can be harder to rendezvous with if there is some slight deviation in their ballistic flight path, which, given that they are traveling thousands of kilometers at thousands of meters per second, there likely will be. And the smaller the object, the harder it will be to track and rendezvous with. Tracking boulders in orbit is easier than tracking specks of dust. So far, we've been assuming a 1-ton payload for our analysis, which, if it were a cube of lunar regolith, would be about this big. and the Navy's railgun projectile was only about 6 kilograms. I have no clue if 10,000 tons or 1 ton or 10 kilograms or 20 grams is optimal. There's too many variables and unknowns, but I do know that 1 ton is nice and round and easy, so we're just going to keep using it. Let's also just assume for now that we just want to launch bulk regolith to orbit. Given that the moon has no atmosphere, our payload and armature does not need to be aerodynamic. They can be square or rectangular, basically a minecart loaded with regolith, flying down the fastest redstone rails west of the Mississippi. Once the armature reaches the end of the track, the front can open, and then if we slam on the brakes, the regolith will fly forward like an unbuckled passenger in an abrupt stop. We can quickly slow down the armature without damaging it from friction using some sort of magnetic braking system near the end of the track, and this will allow us to reuse it once we replace its contacts. Once the payload has been released, it will fly faster than the horizon curves downward, and will reach its apex, apogee, apollune, about 180 degrees on the other side of the moon, from where it was launched. Then its perigee will be where it was launched, which would result in it crashing. So while it is at orbital velocities, it isn't in a true or stable orbit. So it needs to be captured in orbit by a spacecraft to prevent this. All of the systems along the flat end of the mass minimum curve between 50 and 60 Gs have a launch time of around 3 seconds, but we need to account for grid hardware recharge time, so let's assume a 30-second cooldown phase for any of these. With a cycle time of 30 seconds, if it is 1 ton capable, we'd be able to launch 42,523 tons during the 14.5 Earth days long lunar day. Given that lunar regolith is about 42% oxygen by mass, 42,500 tons of regolith yields about 17,850 tons of oxygen. A starship carries 1,500 tons of propellant, 78% of which is oxygen. So that haul could fully refuel 15 starships per month, or about 180 per year. And there's a huge opportunity cost here, because if, on the other hand, those starships were refueled without lunar sourced oxygen, instead using 8 refueling launches, which is optimistic and it may end up being more like 10 or 12, but we'll go with 8 to ward off the hate, then to refill 15 starships from Earth sourced oxygen would require 120 additional launches per month, or 1,440 per year. So an 11,000 ton mass driver can provide as much oxygen to low Earth orbit per year as 1,440 starships. Of course, you need to refine the oxygen and put it in a fuel depot and transport it, so there's more going on than just that, but it gives us a sense of what we can do with just a single mass driver. And the byproduct of this oxygen creation is 24,650 tons of useful metals: iron, aluminum, titanium, manganese, calcium, silicon, and more, all of which can be used to build solar panels and frames and satellites and spacecraft and radiation shields and everything else discussed at the beginning of this video. And so it's sort of a joke to call these things a byproduct of oxygen production, as these will obviously be more useful than the oxygen quite quickly. And I think it's rather more appropriate to think of the oxygen as a byproduct of these things if we are forced to define one side of this coin as a byproduct of the other. Really, there are no byproducts of lunar regolith. It's all useful, and whoever has a mass driver has it all. As always, thank you to the Patreon and channel members who make this work possible. In the next video, we'll talk about induction launchers, coil guns, quench guns, and linear motors. So thanks for watching, stay tuned, and I'll see y'all soon.